Hello everyone! This video is a review of homeworks number 1 and 2 for my Ceramics 1 students here at my high school. If anyone is interested, I will be putting the information of homeworks 1 and 2 in the video description. So students, starting with the basics of clay. Remember that clay is formed from a granite type rock called feldspar. So feldspar is what we're getting our clay from. Remember that it is formed from a process called geologic weathering. It is a natural process. 75% of the Earth's surface either is clay or can become clay. The geologic weathering process has two different types of geologic weathering. One is mechanical weathering, and that is the motion of wind and water that basically abrasively grinds down the particles and creates clay through the mechanical action. The other type of weathering is chemical weathering, where the acids in the clay pretty much just break down the feldspar on the spot, and the acids in the organic matter, it breaks it down, and just right there on the spot it forms clay. So things like swamps, perhaps it's the acidic action, it is when you get chemical weathering. The formula for clay is 1 part alumina, 2 parts silica, and 2 parts water. I'm not going to ask you to repeat that formula in the homework, just as an FYI. Chemical water versus water of plasticity. Chemical water is not wet. The water of plasticity is wet. So the chemical water stays in clay until the clay is actually fired. It has to get to the 1,000-degree temperature in order for it to chemically change, and the chemical water leaves. Imagine if you have cereal, Cheerios. The process of making Cheerios, they add water to it, right? But by the time the Cheerios are made and they're baked and everything, you don't see the water. But it is part of that chemical process. So chemical water is a natural part of the process of clay forming. It is in clay until it gets fired. Now, the wet water that you add to clay to make it perhaps more plastic, that is called the water of plasticity. And that's what, if your clay is a little bit dry and you spritz it down to add a little bit of moisture in your clay recycling bag, or if I am pugging clay and I add water to the pug mill, that is water of plasticity. Hydration is the chemical attaching of the water molecule to the alumina and the silica water molecule. If you've had chemistry, hydration might sound somewhat familiar to you. Let's see, platelets are the particles of clay, and they are shaped like plates or discs. They're flat, and that's why they're called platelets, kind of like blood, right? Clay bodies are developed for control of our 3 major properties of clay, and also to control color. But we want to control the 3 major properties of clay. Plasticity is our first property. That's the ability of a clay to be worked and resist cracking. If clay is not very plastic, it's referred to as short. Sometimes you can remedy it just by adding water. Sometimes you have to add a plastic clay to it, like bentonite. So the clay bodies that I purchase, clay engineers have already figured out what is the good formula to make a nice plastic clay, and they have blended and developed these recipes to create really good usable clay bodies. The next property is the ability of clay to dry without cracking. So plasticity is the ability to be worked without cracking. Porosity is the ability of a clay to dry without cracking. I like to refer with my students to think about you sweat through the pores in your skin. Well, porosity, imagine that the ability of clay to lose its moisture, not really sweat, of course, but you could kind of try to remember that it's drying, it's losing moisture. Now, sometimes you can increase the porosity of a clay by an addition of a non-plastic filler like grog. And grog is just ground up clay that's been fired. So it looks a lot like sand. Sometimes maybe certain sands might be able to be added, but think of grog, it's fired clay, so it can't melt. Some sands can melt. Vitrification is our third property, and that is the stage at which it's fired. So vitrification is the ability of clay to become glass-like, and vitrification is very important in a lot of clays, especially high fire clays. The clay body will melt to the point that it is sealed, it's fully vitrified, it's glass-like, and it is impermeable to water. Now, some of our clays, like earthenware, cannot get vitrified. Earthenware stays porous because the nature of earthenware, if it became fully vitrified, it would physically melt into like a puddle, and it couldn't hold its shape. So vitrification is the property that divides the different groups of clay into high fire, mid-range fire, mid-firing clay, and low fire. It's based on vitrification. The three major groups of clay, or the three types of clay, we are going to be talking about earthenware, which is always low fire, stoneware, which is mid to high fire, and porcelain, which is mid to high fire. Our earthenware is red in color, but sometimes earthenware can be formulated to be white. It just has, I think, more talc in it. The characteristic of earthenware is it stays porous after it's fired, so that's why if you want it to be food safe, it must be glazed, it has to be sealed on the surface, and it is more delicate. Well, it's more easy to chip than, say, a stoneware or porcelain, so you do have to be careful with it. Stoneware is high fire, or in our case, we use a mid-firing stoneware, cones 5, 6, but stoneware has both the ability to be high fire and mid-fire. Our stoneware that we are using here, we have a brown stoneware, and that fires to be like a pink when it bisques and a tan when it gets to the high fire. Stonewares can be really formulated to be any sort of color. I also have a white stoneware in here. I have like a black stoneware that sometimes we use in the upper levels for a pick a passion. And stoneware can, again, a wide range of colors. Let's see, it is more durable than earthenware, and stoneware can have grog, or maybe it can be without grog. So you can have it either way. Again, these are formulated clay bodies. Porcelain is high fire and mid fire range. I have a little bit of porcelain that I buy, again, for upper levels in pick a passion. Porcelain is not as plastic to work with, so it's a little bit more challenging for beginners. So when you're working with porcelain, you have to be very attentive to the drying to try to not have cracking and things that might happen with careless craftsmanship. It was originally developed in China from kaolin, the clay kaolin, and sometimes if you just hear people refer to like fancy dishes as China, that's because it's usually in referencing porcelain, which originally was developed in China. So that's why we call China today as just fancy dishes that are porcelain. A little bit of history. So some of the earliest fired pieces that we know of are little figurines, like little goddess type figurines, and also rustic vessels. Sometimes some of these may have just been fired over campfires. We don't really know how it developed, but maybe it was accidental. You know, clay pressed into baskets may have started something like that, and it fired in a campfire, and suddenly they had a pot. We're not really sure. Clay is refractory, and the term refractory means it has resistance to heat or melting. So some items that are made from clay today are made because of their refractory ability, such as spark plugs in an automobile. Kiln shelves and kiln posts that we have in the kiln room are also refractory. If you ever take a look in there, you'll see that they are very high fire clay and they withstand the heat of firing in the kiln. Plaster, glass, and cement are also important ceramic materials. We just typically deal with clay in here, but sometimes we deal with glass and glass fusing and also plaster. Using clay. For clay to be usable, we often will need to wedge it into a workable lump, especially if you have scrap pieces. You will need to kind of combine your pieces together to make it a nice, even moisture consistency. The term ware means pots or pottery. A lot of times I will refer to things in here. I'm not making up these words. They are legit words, like our ware carts, where we put our pots, ware boards that we might put our pots on when we put them in the cabinets. And then one of the huge things that you have to remember is when you are glazing a piece, the glaze and the clay body must always be compatible. They are going to be fired to a very specific cone or a temperature. We'll talk more about pyrometric cones in another homework, but a cone gives you a temperature range that you're going to be firing to. So the glaze and the clay body must always be compatible. Our kilns that we have here at the high school, they are fired with electricity. They have little elements around the interior which heat up like an electric oven, and when it heats up to temperature, it will be close to 2,000. Our kilns here at the high school are all operated by electricity, with the exception of the Raku kiln, which is out on the patio. That one is natural gas. So our electric kilns inside, they all have elements in the wall which heat up during the firing of the kiln. There's no physical fire in my kilns. They just are heating up just like an electric oven would to bring it up to the final temperature. Our kilns could get fired to as hot as like 2,220 degrees, which is cone 6. A lot of times I fire it to more like around 1,800, 1,850 for our bisque temperatures. So cone is short for pyrometric cone. We'll talk more about those in another homework, but pyro meaning heat or fire, and metric meaning measurer. It's the measurement of the heat in the kiln. So the pyrometric cones are the how we refer to how hot we're firing the kilns. So a low fire clay body might get fired to cone 04, 05 with glaze. The mid fire that we use gets bisque fired to cone 04, and it gets glaze fired to cone 6. So it's much hotter. And again, we'll talk about that more. I just want you to know that cone refers to temperature. If clay is fired too high or too hot, it will melt into a puddle. So contrary to what a lot of people think, it doesn't blow up if it's fired too hot. It physically melts, and it can destroy a kiln. The kiln, of course, is the chamber in which we heat the clay. Firing has to occur pretty slowly, especially during the bisque firing. When a bisque fire is the first firing, you have to make sure that all the water vapor is gone from your pieces before it gets up past 212 degrees. You might know that at 212 degrees Fahrenheit, water turns to steam. It will boil and turns to steam, and it's very explosive. So we have to make sure that the pieces are very, very dry. If they still have water vapor in it and it goes above 212, it will blow up in the kiln. One of the things that I tell people is never exceed, say, like 3/4 of an inch thick in your thickness of your pieces. That way I can ensure that it will be able to dry enough to get fired without blowing up. If you do have to exceed 3/4 of an inch in thickness, perhaps you could vent it with vent holes in an inconspicuous area to make sure that it can lose all the water vapor and the moisture. If you have any trapped air, like you have a hollow sphere, I usually tell people to vent it. Not that it's 100% absolutely necessary, because if it's dry, it shouldn't blow up. But sometimes in the classroom setting, I tell people to vent it because we still don't want any trapped moisture within a hollow sphere that would blow it up. So students, I hope you just read over that homework, do your best on the quiz, and I'll see you in class.